2211, and I did analyzing the falling Slinky. So the purpose of this lab was to predict the motion of a falling Slinky and analyze the effects of its surroundings, as well as take a look at how both the ends of the Slinky act when it is dropped from a certain height. The models used in this experiment was the video analysis software called Tracker that allowed me to track the object's position over time accurately, as well as the computational simulation using ClosScript and Python. The principles showcased in this experiment was the momentum principle, also known as the Newton's second law of motion, the drag force, and the gravitational and tension forces. And a quick preview of the results. Although there were minor discrepancies between the models, the bottom of the Slinky did remain stationary throughout its motion. So here are the physics principles. First, we have the Newton's second law of motion, which basically shows that a system's change in momentum is proportional to the net force applied, and you can see that here in this equation where the net force is equal to the rate of change in momentum, and that in turn, with some simple calculus, shows that it is equal to the mass times acceleration. Then the drag force here is the resistance force caused by the motion of a body through a fluid like air or water, and it is always in the opposite direction of the object's motion. Here, the drag force can be exemplified by the equation negative b v squared times v hat, where b is the proportionality constant of the drag force, v is the speed of the object, and v hat is the direction of the velocity. And here we also have our gravitational and tension forces acting on the Slinky, where the bottom end of the Slinky is being pulled down by gravity, while tension in the rest of the Slinky is pulling it up. So it is remaining in the same position because the net force acting on it is 0. And because of this Newton's second law of motion, the net force is proportional to the change in momentum. And if the net force is 0, the change in momentum is also going to be 0, and therefore the object is not accelerating. So here is a representation of the Slinky's motion as it is falling, and we can see how the bottom kind of stays in the same place, but this will be exemplified more by our analysis of the video as well as our computational model. But here we can see in this video that the system is the Slinky, and then the surroundings are the hand that is dropping it as well as the earth. So here is our observed motion and our video analysis results by plotting the position of the Slinky at each timestamp using Tracker. The initial conditions here was the mass of the Slinky, the initial position, and the initial velocity, which was 0 because it was being dropped from rest. So here in our computational model, we can see we input the Slinky's mass as well as the initial position and velocity vectors, as well as the drag proportionality constant down here. And then in our first while loop, this is the while loop while the bottom of the Slinky is remaining in the same place. Here we have our velocity and position update formulas, and also are calculating the net force, where we have the effect of gravitational force as well as the tension force, which is directly opposite of the gravitational force because the net force is 0, so they cancel each other out here. And then again our velocity and position update formulas. And then this is our second while loop, which is after the top of the Slinky evens out with the bottom and then they start falling together. We can see here that the net force is no longer 0 because the Slinky, the bottom of the Slinky is accelerating. So the net force is no longer 0 due to the Newton's second law of motion, and then we still have our velocity and position update formulas here. So there were discrepancies with the model because, as we saw in the Tracker graph, it did seem like it was moving a little bit, but there are possible causes for these errors. There could be external forces that were acting on the Slinky that we didn't account for with our computational model, as well as inaccurate tracker placement of the points on my part. And here are a few more discussion questions that we want to talk about. So why does the bottom of the Slinky remain stationary? So again, that is because while the bottom of the Slinky is being pulled down by gravitational force, the tension force is acting in the opposite direction of it, and until the top reaches the bottom, that tension force cancels out the gravitational force, therefore causing the bottom of the Slinky to remain stationary. But what if we did attach a weight at the bottom of the Slinky? Would that cause it to still remain in the same place, or would it be falling down faster? So that really depends on the length of the string of the Slinky, the relaxed length of it, as well as the tension, because it could be the tension force could be greater if it was a more stiff Slinky. So it really depends on those factors, whether the weight would be enough to be greater than the tension force in the Slinky and be moving down faster, or if it would still be canceled out with the gravitational force that's pulling down on it. And in conclusion,